Welcome back to our journey through dynamic topology. We're continuing this series from the Staiblocks channel, diving deep into Gordon Whyburn's incredible book. Today, we're going to forge one of the most essential tools in any topologist toolkit, a way to mathematically define what it actually means for a shape to be in one piece.
So take a look at these two shapes. Intuitively, you just know one is a single continuous piece and the other is broken, right? But how would you prove it? See, in mathematics, saying it just looks that way doesn't cut it. We need a rigorous, undeniable definition for this idea of being connected. And to get that proof, we need a really powerful tool. Topologists needed a formal way to capture this intuitive feeling of oneness, and what they came up with was the brilliant concept of a connected set. Okay, I know this definition looks a little intense at first glance. It's packed with all these terms like disjoint, union, and limit points. But trust me, the idea it's describing is actually incredibly elegant. It's a classic mathematical move. You define something by what it isn't.
So let's translate that formal language into something we can really grab onto. A set is connected if you just can't tear it into two pieces, A and B, that are complete strangers to each other. For a set to stay connected, those pieces have to touch, meaning one piece has to contain a boundary point, a limit point of the other. There can't be any gaps. And this quote, wow, it really gets to the heart of Whyburn's whole philosophy. He didn't want his students to just memorize definitions. He wanted them to build their own proofs, to make these tools part of their own working equipment. So in that spirit, let's put our new definition to work. This is such a brilliant way to show the power of our definition, using a classic proof by contradiction. Let's just walk through it. So, step 1, you see our setup, a bunch of connected sets, and they all overlap at one common point. Now for the trick in step 2. We assume the exact opposite of what we want to prove. We say, okay, let's pretend their union can be split into two separate parts, A and B. Well, that common point has to go somewhere, right? So in step 3, we'll just say it's in part A. But wait, since every single one of our original sets contains that point, and they're all connected, none of them can be split. This means they all have to get sucked into part A, which you see in step 4. And here's the punchline in step 5. What's left for set B? Absolutely nothing. It's empty, which totally breaks our initial assumption that B was non-empty. Our assumption was wrong. The union has to be connected. How cool is that? We've just proven we can build bigger connected shapes from smaller ones. So up until now, we've been looking at sets as if they exist in a vacuum. But what happens when we change our perspective? What if we zoom in and only look at a shape within a smaller piece of its universe? This is the huge question behind relativization, or what's known in topology as the subspace topology. We're basically asking if a shape's properties are absolute, or if they depend on the context of the space around them. And it turns out, context is everything. Think about it this way. A small patch of grass might not be considered an open field if you're looking at a map of the entire country. But if you're only looking at a single dense city block, that patch of grass might be the only open space around. Topology works the exact same way. A property like openness can be completely relative to the space you're considering. But, and this is a really big but, connectedness is different. It's what we call an intrinsic property. A shape is either in one piece or it's not. Period. You can't make it disconnected just by changing your point of view. It's like its genetic code. It doesn't change just because it moves to a new city. This makes connectedness an incredibly robust and reliable property to work with. All right, now for a really deep question. We've defined our set, but what about its shadow? What about the ghost it kind of leaves behind in the space around it? I want you to imagine a connected shape. Now think of all the points that are infinitely close to it, points on its boundary that you can get closer and closer and closer to, even if they aren't technically part of the set itself. Those are its limit points. So the big question is, if we gather up that original shape and we add all of these boundary points, do we accidentally create a gap? Do we break the connection? And the answer is a resounding no. The connection is so fundamental that it actually extends to its own boundary. This combination of a shape and all its limit points has a name. It's called its closure. And the key theorem here is just fantastic. If a set is connected, its closure is too. You cannot break a connected set by adding the very points it's trying to reach. So let's zoom out. We've defined connectedness, we've tested it, and we've seen just how robust it is. What's the big takeaway from all this? Why does it matter? It matters because we've gone from just a vague feeling about a shape to a rigorous, powerful mathematical tool. We can now describe, prove, and build with the concept of oneness. We've uncovered something fundamental about space itself, that connectedness isn't just a visual trick, it's a deep structural truth.
Honestly, this is just the beginning. Now that we have this powerful tool in our hands, what's next? This definition of connectedness is the key that's going to unlock even more complex and beautiful structures, things like continua and mappings, which is exactly where we're headed in our next explainer.